So what exactly is SAMP? SAMP is a free and open source platform that provides everything you need to set up a local server on your computer. It bundles together Apache, MySQL, PHP, and Perl, so you can run website and web application locally without needing an internet connection or a remote server. Whether you're developing in PHP, testing databases, or just need a simple server setup, SAMP is a great solution. Now, let's dive into how to install it. To install SAMP, first head over to the official SAMP, www.apachefriends.org. You'll see a download button right on the home page. Choose the version that matches your operating system. Windows, Linux, and Mac OS are here. But for this demo, I'm going to show you how to install SAMP on Windows, but the process is very similar on Mac OS and Linux. Just click what version you want and click download button. Once the download is complete, open the installer. You'll see a security warning asking if you want to allow this app to make changes to your device. Click yes to proceed. The installer will walk you through the setup process. Just click next to get started. On the screen, you can choose which components to install. By default, all the important ones, Apache, MySQL, PHP are selected. You can leave this checked unless you want to customize your installation. For most users, it's best to go with the default setting. Click next to continue. Next, you will choose where to install SAMP. The default folder also should work just fine, so click next again. Next, click next. The installation process will begin. It may take a few minutes, so just sit back and relax. Once the installation is complete, click finish to close the installer. At this point, you'll see the SAMP control panel pop up. So this is the SAMP control panel where you can manage your server services like Apache and MySQL. Let's start them up now. Just click start next to Apache and MySQL. And that's it. You've successfully installed SAMP. Now you have a fully functional local server on your computer. Test it out. Open your web browser and go to localhost, or just click the admin button in SQL. You should see the SAP welcome page confirming that everything is working as expected. And that's the basic installation process. Now you can start developing your project locally and test everything before moving it to a live server.
History of database. Early computer era, 1950s to 1960s. The concept of organizing and storing data in a structured manner emerged during the early days of computing. These were the use on a period of early computers. Key technologies were IBM punch card, Univac magtape, IBM mainframe computer, and hierarchical database model. So basically, during this point of time, people started to realize that they could use computers to organize information instead of writing things down by hand. They could punch holes in cards or use magnetic tape to store data. These were early databases were a big improvement, but they were still complicated and unreliable. The relational era, 1970s to 1990s. Edgar F. Codd introduced the relational database model in his groundbreaking paper, A Relational Model of Data for Large Shared Data Banks, in 1970. IBM System R and Oracle were among the first relational database management system, RDBMs, to implement Codd's idea. Codd's relational model revolutionized database design, and SQL became the standard query language. To quickly summarize this era, it became a lot easier to use and look for data using SQL by talking to databases, and then companies started selling database software, making it available to more people. 1990s, rise of client-server architecture. In the 1990s, databases became more distributed and scalable thanks to client-server architecture. This also led to databases handling more complex data types through object-oriented models. A common example of this setup was Windows NT and its server counterpart. The post-relational era, 2000s and present. The rise of the internet and web applications spurred development of NoSQL databases like MongoDB and Cassandra. By the 2010s, big data technologies such as Apache Hadoop and Spark emerged to process massive datasets, while cloud databases became increasingly popular, offering scalable, flexible solutions for managing databases in the cloud. So basically, it became a common example to set up cloud computing to store and access databases over the internet. The intelligent era, present and future. Blockchain technology introduced decentralized and distributed databases, providing transparency and security for applications like blockchain transaction ledger, machine learning DB diagram, and edge computing IoT data flow. Databases are becoming more autonomous, scalable, and adaptable, playing a crucial role in supporting data-driven applications and enabling real-time insights. Focus on performance, scalability, intelligence, security, and decentralization. To basically sum this era up, databases are getting smarter, they use AI, and databases can handle even bigger amounts of data and work in real time. This era is like having a personal assistant who can anticipate your needs and help make your decisions better. And that is the end of the database history.
Database and key components and concept. Data. Data is a facts, figures, text, image, or other types of information. Also, data is organized into tables, rows, and columns. Example, an online bookstore organizing books by title, author, and genre. My explanation is, in an e-commerce system, customer information is crucial for managing orders, providing personalized experiences, and ensuring smooth transactions. This data is typically stored in a database using structured tables. Number two is table tables. Table is a fundamental component of a database consisting of rows and columns. Example, a customer's table with columns for ID, name, and email. Trivia: the first commercial database, IMS, was used to track Apollo space missions. Number three, rows, also known as record or types, they contain the actual data in entries. Example, a row in the customer's table representing a single customer. Trivia: a single row in a table can hold data for multiple columns, making it a unique data entity. My example is IBM's Information Management System. IMS is one of the earliest commercial database management systems. It was developed in the 1960s to help NASA and its constructors management complex data related to the Apollo space program. Number four is columns. Columns is also known as fields or attributes. They define different data types stored in a table. Example, column in the customer's table might include ID, name, and email. Trivia: each column has a specific data type such as text, numeric, or date. In a database, a column, also called a field or attribute, stores a specific types of data or each row. Each column is assigned a data type which defines the kind of values it can hold. Data types help ensure data integrity, consistency, and efficiency stored. Number 5 is fields. Field is an individual data element in a record representing specific properties or characteristics. Example, the name field in the customer's table. Trivia. Trivia is in a database. A field is an individual data element within a table representing a specific property of an entity. Fields are defined within columns and hold values for each row record by enforcing data consistency and structure. Fields make it easy to retrieve and manage information efficiently. Number 6 is case. Key is a unique identifier for records within a table. Example, a primary key for the customer's table is the customer ID. Trivia. Foreign key, like the primary key of one table to a column in another table to establish relationships. And my explanation is a foreign key is a column or a set of columns in a one table that references the primary key of another table. This relationship is maintained the integrity and enforces referential constraints between the two tables.
Okay, next. Relational database. Case is a unique identifier for records within a table. Example, a primary key for the customer's table is the customer ID. So, in a relational database, a key is a unique identifier used to distinguish each record or row in a table. It ensures that no two records have the same value in the key columns, helping to maintain data integrity and prevent duplication. So that's a relational database. So next, database management system. DBMS is a software providing an interface for interacting with a database. Example, MySQL, Oracle, and SQL Server. So a database management system or DBMS is a software that allows user to create, manage, and interact with database. It provides an interface for, for storing, retrieving, and updating and deleting data while ensuring security, integrity, and efficient data handling. So next, structured query language. SQL is a language used to communicate with the relational databases. Example, querying data with select asterisk from customers. So, structured query language or SQL is a standard programming language used to interact with relational databases. It allows user to store, retrieve, update, and delete data in a structured way. SQL is essential for managing and manipulating database records efficiently. So that's a SQL. So next, normalization. DBMS is a software providing an interface for interacting with a database. Example, MySQL, Oracle, and SQL Server. So normalization is the process of organizing data in a database to reduce redundancy, or duplicate data and improve data integrity. It involves dividing large tables into smaller, related tables and defining relationships between them. So next, indexing. Indexing is a technique for optimizing data retrieval. Example, creating an index on the email column in the customers table. Indexing is a technique used to optimize data retrieval by making searches faster in a database. It works like an index in a book, allowing the database to locate records efficiently without scanning every row. So that's indexing. So next, lastly, transaction. So transaction is a sequence of database operations executed as a single unit. Example, transferring money between bank accounts as a single transaction. So a transaction is a sequence of one or more database operations that are executed as a single unit. So it ensures that all operations within it either complete successfully together or fail completely. So maintaining data integrity and consistency. So that's all.
Important reasons why we need databases. Number 1. Data organization. Structured way to store and retrieve information. Example naman ito, an e-commerce site organizes product data into categories, making it easy for customers to find items. Trivia guys, ang first digital database ay na-create noong 1960s to manage data for the US Census. So next, number 2, data retrieval. Quick and easy extraction of relevant information. Example naman ito, a library database allows user to search for books by title, author, or genre. Trivia naman dito, SQL is the standard language used for querying databases. Next, data integrity. Data integrity ensuring accuracy and reliability. Example, a healthcare database enforces data integrity rules to ensure patient records are accurate and up-to-date. Trivia naman nito, data integrity helps prevent duplicate records and maintain accurate information. Next, data security. Data security protecting sensitive information. Example, an online banking system uses encryption and access controls to secure customer account information. Trivia naman dito sa data security ay encryption converts data into a secure format that unauthorized users cannot read. So, next naman tayo ay itong number 5. Concurrency control. It is managing simultaneous access by multiple users. Example, a collaborative editing tool ensures that multiple users can edit a document without conflicts. So, ayun guys. Trivia naman, concurrency control prevents conflicts and maintains data consistency.
Six. Scalability is a database that can scale to accommodate growing data and user demands. Examples: expanding a social media platform's database to handle millions of users. Trivia. Horizontal scaling adds more servers, while vertical scaling adds more resources to an existing server. Means they can expand to handle more data and users as needed, ensuring the system works well even when demand increases. 7. Data relationships are databases establish relationship between different data sets. Example, linking customers and their orders in an e-commerce database. Trivia. Relational database is used primary and foreign keys to create relationships, or data relationship in databases refer to how different sets of data are connected, allowing for better organization and retrieval of information by linking related data across multiple tables. 8. Data independence. This database provide a layer of abstraction between applications and data storage. Example, changing the database schema without affecting the application code. Trivia. The data independence allows for easier maintenance and upgrades. Means that databases allow change to how data is stored or organized without affecting the applications that use that data, providing a layer of separation between the two. Number 9. Data redundancy reduction is database minimize data redundancy by storing each piece of information once. Example, storing customer information in a single table instead of multiple places. Trivia. Reducing redundancy decreases the chance of data inconsistencies. Means that databases are designed to keep each piece of information stored only once, which helps save space and avoid confusion from having duplicate data in multiple places. Number 10. Data analysis and reporting is database for support complex queries and reporting functionalities. Example, generating sales reports from a retail database to analyze trends. Trivia. Data analysis helps organizations make informed decisions and gain valuable insights. Means that these systems are designed to handle complicated questions and create detailed reports, allowing users to get insights from large amounts of data easily.